Well, welcome to my presentation, uh, my seminar webinar, which is going to be today. We're going to talk about anchors, bolts and nails. We're going to talk about soil nailing and tieback walls as well. My name is Alberto Ortigo. I'm a geotechnical engineer with over 50 years of experience, and I hold a PhD from University of Rio, PE in America, in a few states, and also I'm a fellow and a charter engineer of the Institution of Civil Engineers in London. And well, let's get started. So the what we're going to talk in this first part. We divide into three presentations. In the first part, uh, well, I'm going to talk a little bit about the tieback wall and soil anchors, which started, as far as I understand, my professor Costa Nunes at the School of Engineering was the first to use that in 1957. We're going to talk about that. We are going to talk about concrete reinforcement with steel bars, threaded bars. That's the way it developed today. In most projects, we use threaded bars. And of course, we can use also multi-strand anchors. We're going to talk about that. And we're going to talk about corrosion protection, grouting, testing, and soil nail friction. So that's the introductory part to the tied back a soil nailed wall. The first, as far as I know, the first tie back wall was designed by a professor of mine from the School of Engineering. I'm going to discuss this a little bit. And he used to say when I was a student that was the first uh, tieback wall in soils. Until then, the Germans had used tiebacks or ground anchors in rocks, but he used to say that was the first 1957. And the idea is that for this kind of wall, we have an active reinforcement. What does it mean? That we pre-stress all the tiebacks to a maximum working value, and so they are all pre-stresses. So with this, we reduce a lot of displacement that may occur. On the other hand, the passive reinforcement was developed much later, I think in the mid 70s. Uh, and it's the difference that the passive the passive nails, they are not pre-stressed. They are left with a very small pre-stress, almost nothing. And how do they develop uh, the behavior, or I mean the stresses? When the active wedge tends to move, then it mobilizes stresses, shear stresses alongside the nail. So that's when we have nail friction. So these are very different concepts. This was developed, as I said, the first one I know is from 1957. This one maybe in the 70s, and now both are very much used depending on the application. The main difference between the two is that we have the, as I've said, uh, active reinforcement, and then the displacements with the tieback wall tend to be less than the soil nail effect. The rebars, the first in the first say 10 years or 15 years, uh, these anchors were made with rebars. I mean, concrete reinforcement bars. That was the trend, and much later they started to have threaded bars. So these, in most cases, I've seen in the past, the diameter of these rebars was about 25 millimeters. The steel grade was a very low steel grade, which was used in structural engineering at the time. the CN25. This steel strength of this steel is only 250 megapascals, which is small, and the testing load was about 1,000 kilonewtons, and the working load about half of that value. That was a few projects which I've seen of those of that time, and usually no corrosion protection in the early days because people didn't realize the importance of that. And of course, now today we do completely different, and I'm going to show you that. In the mid 70s, that was the first time I've seen manufacturers providing threaded bars. These made they work much easier because before we had to do the threads on the steel bar. Then the mid 70s they started providing this kind of threaded bars, which made the work much easier, much better connection, much faster. Of course, a little bit more expensive, but worthwhile to have that. And so you see here the threaded bars, the spacer, the connectors, and the head, uh, uh, the head with the plate and nut, okay, for the threaded bars. Now there are several manufacturers doing that. The other aspect I'd like to call your attention is the need for a manchette valve. Manchette valve is the name of the valve that uh, is usually made to allow you grout the tie back, so the ground anchor. Okay, so usually this is a rubber band. In the past, people used to use a bicycle tire to do that. Okay, and these are the manchette valves, and this is the grouting tube alongside the threaded bar. And some years later, people became concerned with corrosion protection, and there are several ways of doing that. So you have here an example in which you have here the free length, the grouting tube, and this part of the bonded length is resin coated bonded length in order to avoid uh, corrosion or to limit corrosion. Of course, we have here the centralizers. These centralizers, in many situations, are made at the site with PVC pipes. You know, very easy to make. So we have by having this kind of centralizer, we make sure that the bar, the seal bar, is in the middle of the borehole. Okay, so the different types of centralizers I've seen. This is a locally on-site made uh, centralizer, okay, with the PVC pipe, and also these resin-coated bonded length for corrosion protection. One of the types of corrosion protection that can be used. This is an example of this centralizer being made at the site. Rate of corrosion is very important you to account for this. When you are in the countryside, the maximum corrosion rate is very small. But when you enter in an industrial site, industrial area of a city, you may have much higher corrosion rates, and that's when this is very important. The other thing that's very important is when, yeah, like this tieback wall is on the sea by the seafront, and of course corrosion rates here are very high. And this is one inspection I have made in the past, so you see how corrosion was important in this place. This has been restored, rehabilitated this tieback wall. And in the past, the multi-strand anchors were used. What's the advantage of multi-strand anchors? You may have a much higher load capacity for these ground anchors. The problem in the past, perhaps not today as used to be, is corrosion. Okay, so I've seen along my life things like that. You know, the strands were all corroded like this, terrible situation. Okay, to the point that when we wrote many years ago, 20 years ago, the slope manual, uh, our recommendation at the time was not to use multi-strand anchors for permanent structures, okay, only for temporary structures. Recently, DVDAG and perhaps other manufacturers, as I'm going to talk later on, they developed ways of dealing with corrosion for multi-strand anchors, as I'm going to say. So, as you see, it was a catastrophe using these multi-strand anchors for permanent applications. And so today, many standards have different levels of corrosion protection, like single, just epoxy coating and grout, uh, double epoxy coating, corrugated plastic sheath, and grout. And this can be applied to places where you may have very high or small corrosion protection, okay, rates, corrosion rates, okay. And this is something that I have used in the past for places where I found corrosion could be a big problem, especially industrial sites or seasides close to the sea. And we use a double protection in which we have the steel bar is completely surrounded by this corrugated plastic sheath, and the could be epoxy coated as well. And here we have grout in between the bar and this corrugated sheath. Uh, and this is an example. Uh, as you see here, the steel bar, grout, and the plastic sheath. Uh, these are another idea that for multi-strand anchors they had kind of corrosion protection with these uh, tubes or pipes in which they are filled with uh, grout or even grease. But some places do not need that amount of corrosion protection, and epoxy coating could be uh, acceptable. In Hong Kong, for instance, they use galvanization. Okay, I've worked in Hong Kong long ago, and this is considered more than enough in that city in that manner. So here's a typical Hong Kong nail, okay, with the grouting tube and centralizer, and the fact that it's galvanized, okay. And this instrument is used to measure the thickness of this protection with galvanization, okay. Uh, bonded length, uh, these are different type, where you see here the centralizer, the grouting pipe, and corrosion protection by treatment, epoxy treatment. And here an example of DVDAG. DVDAG is one of the major manufacturers available in many countries in America as well, Canada, etc., all over the place. And here you see the free length, the bonded length, the centralizers, and the grouting pipes, as you see here. Well, loads. We have to define two different types of load: the maximum load, the testing load, and the working load. So the testing load, usually the oldest bars are tested to 90% of the yield load. The anchors, when after placing the anchors, we test all of them to 90% of the yield load of the steel. And the working load varies according to the standard. There are standards which uh, we divide the test load by 175, and this should be the working load. Other standards prefer to use the two. Okay, it varies, but one one or the other would work very, very nicely. And here are some examples of today's developments. For instance, DiviDog, as I've said, is a major world manufacturer of these ground anchors. Here we see how they provide it's totally corrosion protection. They have these spacers, etc. Here's a threaded bar, and here are values of working load from say 350 to 1100 kilonewtons. Okay, uh, so if you need more than that, perhaps you would have to go to the multi-strand anchors. Here's a temporary ground anchor, also by DVDAG. The level of corrosion protection is not that much, okay? And these are permanent multi-strand anchors in which DVDAG announces that you may have very high loads. Okay, they go up to here the working load 1,000 about 1,000 kilonewtons. Not much, not very different from the steel bar. And here's a temporary multi-strand anchors with much less, uh, almost non corrosion protection. Okay, and nails, soil nails with corrosion protection or less. Okay, we have these are the working loads of these DV bars. Uh, Cement grout. Uh, uh, what you have to do, you should have a grout with a water cement ratio of less than 0.5. Okay, you may use admixtures for swelling to setting accelerator to do it very fast. And all you need is these high turbulence mixers in order to prepare the grout. And what's the goal in terms of strength? That with the 7-day testing, you should have strength over 25 megapascals. Okay, so that's usually the goal. You for these ceramics you have to use grease in the free length. So to avoid the grease is to avoid contact with water and water ingress. Self-healing, they should be the grease should be self-healing. Thixiotropic, I mean they should be self-healing, and also they should be microbiological activity resistant. And an example of these greases is Shell's Ferroprot 4450. You know, I did a long time ago. I did a market search and I found this one, which may be used. And this application of grease at the bonded length, the free length, I mean, not the grease is applied on the free length, of course. Okay, and in my experience, where you have to take into account the corrosion, the big possibility of corrosion, which I've seen, in two things. One at the head of the tieback walls, which I'm going to address how to deal with that, and the other one is a very important one when you have this kind of rock bolts and you have a preferential seepage path for water here, or you have jointed rocks, okay, in which you may have a very high rate of corrosion at these points here, this point, this point, and this point. So these are the points that you should take care because corrosion could be a big problem. Okay. Final stages. How to avoid corrosion. Repainting steel parts at the head of the ground anchor. Head protection, which I'm going to show you. Post-grouting of the head. This is very important. And how to do that? Usually, what you can do is to leave a grout pipe here when you cast the head. These is concrete. So by leaving this grout tube here, you can come back and pour additional grout, okay? And you just fill all the voids here with grout, and then you avoid corrosion. However, there are situations in which the level of corrosion can be so high that fiber reinforced plastic nails, the FRP nails, could be used. And there are a few manufacturers. This is one manufacturer from Switzerland, which I visited many years ago. And what are the advantage? High and adjustable tensile strength, high and adjustable Young's modulus, high dynamic strength, excellent corrosion resistance. You don't have to care about that anymore. Low unit weight, magnetic and electric neutrality for applications. One of the very interesting applications of these bars are in hospitals where you have this equipment, EMR, etc. So you can't have any steel around. So these bars can be used. I remember this, and easy to cut. Okay, but there are some catches. This is steel, common concrete steel with a strength of 500 megapascal, the CA50 grade. These are pre-stressed wire, okay, much higher. So you're going to have a tensile stress much higher, about nearly 3 times, okay? Carbon fibers. Carbon fiber has enormous strength. And also glass and aramid as well. Less, a little bit than carbon. But so if you compare, for instance, FRP with steel, so here's the strength of FRP in blue and steel in red. So it's about twice what you get. The modulus, on the other hand, is very small, young modulus, and unit weight also very small as compared to steel. But what is the big problem of using this? It's not the tensile stress, it's a shear stress. Shear stress. So the design of these heads is much more complex, okay? Because you can cut, and also the shear stress here, the shear resistance of those bars are much less. So these are some examples of FRP made by DVDOG. So they have the solid bars, the hollow bars with the drill bit. Okay, there are some interesting applications where you may have a very high corrosion rate, or in tunnels, which I'm going to show you later. And here, the what tensile failure load for these bars in terms, it's about 1,000 kilonewton, even for 32 millimeter bars. But the maximum head load is much lower because it's very difficult to design this to have. So you have a lot of tensile strength, but maximum head is much lower. These are the disadvantage, and shear failure load is very small. Okay, this is the problem. These are another manufacturer, the MST. I think they have a factory in Canada. They are supplied in America as well. So they have also designed the heads with this steel steel tube here, pipe, which allows them to increase the maximum loads at the head, but still very low. Okay, very low as compared to the tensile strength of the bar. Here an example of FRP for soil nailing, okay, in which they used geogrids and FRP nails, so no concrete. This is an example, can be done, not very, I haven't seen that too often, but can be done. One very interesting application of these FRP nails are during tunnel, any ATM tunnel sites construction, in which you want to reinforce the face of the tunnel during excavation. So I have used this in a few projects and very successfully using this FRP. And why FRP? Because it's very easy to cut. So when you excavate, it's very easy to cut. On the other hand, if you have steel, it's a big problem. You must have a weld, etc., and the torch to cut the steel. So it's additional equipment, and it's a little bit dangerous to use inside the tunnel. So FRP for this application can be perfect. Okay. The other thing I'd like to discuss with you now is friction on anchors and nails. Okay, for the design, if you want to do a proper design, you must uh, have knowledge of the friction that could be applied to the nail of the anchor in order to design the length of the anchor of the nail. So usually this is the kind of assembly that you should have for the tests. Okay, so you have usually 1 meter free length and 2 to 3 meters of grouted or bonded length in order to pull this out. And here you have a jack, hydraulic jack, and a load cell, absolutely necessary. And here a dial gauge in order to measure displacements. And this is the kind of arrangement that I have used in the past. So I have the jack here, and here's a plate that we use in between on the sides of the load cell in order to distribute the load. This usually a 5 centimeter thick plate, and here another arrangement, okay, with a different setup, and this is to hold the dial gauges in order to measure the displacement. And when I started designing the nails, that was my first project was 1991, or less of this time, so many years ago. Uh, we didn't have any correlation apart from those which were proposed by these two French guys, Bustamante and Dois, in 1985. They proposed this correlation between uh, this is the uh, uh, limit pressure from the pressure meter, and this is the N value, the SPT value. So in which we could come here and obtain the QS, which the soil nail friction. Okay. The problem is that in most cases I have worked in the past, we had SPTs of say 10, 20, something like that, not more than that. And the scatter of the results in this for these SPTs were very, very high. We can come up with a value, say, of nearly zero point 0.2 megapascal, or nearly zero from zero point 0.2, or perhaps 0.5, 0.2. This is too much, okay? And they have this correlation for sands and for clays as well. For clays, is even the scatter is even higher. And one of the I started using this technique, the soil nailing, uh, 1991, 92, and the one of the big projects that I've used this was the Brazilian Underground, which was built. It was a 6 kilometer tunnel built in between 1993 and 94, and I worked as a consultant to the during construction, and we used in a few cases soil nailing in this project. And the what's interesting here, this is the geology of Brasilia. It's a 6 kilometer long tunnel, and we have a very weak clay. I'm going to show you SPT of 2, 3 maximum. And here's the meteoritemite. Meteoritemite is uh, it's a sequence of uh, sandstone and siltstone usually. And here we have slate. So uh, This is a typical borehole in the Brazilian porous clays. As you see, the metal-rich minus the SPT is much higher, a minimum of say 10, and then turns out to be a rock, while the porous clay in Brasilia, it's about only 2, 3, maximum 5. And this is the first time I managed to find the contractors to carry out lots of tests for me. I arranged this with the organization of the Brazilian Underground, and we did a lot of tests, like varying the diameter of the borehole and coming up with uh, what should be the QS, the friction, uh, nail friction in this material, because you didn't have any correlation for that, and that was very interesting. So the mean value of the QS, which was 50, 60 kilopascals, was independent of the diameter. And then we did a lot of tests, not only in the porous clay, but on the slate saprolites, where we had to, oh dear, something happens. What shall I do? Ah, sorry. Mm, I need help. Something went wrong. Let me see.
Better try escape.
Escape, okay.
Or if that doesn't work, unshare the slides and share them again.
Okay, stop share, and
Yes.
I share them again. I'm sorry. Oh dear. Stop share. I do it again. I'm sorry about that. Okay, sorry about that. No, this one indeed. That's not the one. Sorry again. Unloading it. Okay. Okay, sorry about that. Something happened. I don't know what. But so we have carried out a lot of tests, and this is the range of values in which the uh, here the porous clay we have a range 50, 60 kPa, and there was a big variation, a big difference between the mix and maximum value at the slate saprolites, which are much harder material, but a minimum of 100 and a maximum of 200 kPa. And then I started developing this kind of correlation with a few a few sites, okay, and we published this data in 1997. So the purpose was to optimize design of soil nailed walls. This was published in London, and we came up with a correlation that we still use between the NSPT value and the QS. Okay, we have a suggested lower limit, 9% lower confidence limit, and this is the correlation that we came up with. Okay, between the SPT and the QS, and it works. I can assure you that it works nicely. For rocks, there are interesting recommendations that I use, in which QS is 130 of the unconfined rock compressor strength, or the 130 of the unconfined compression strength of ground specimens. So in most cases, if you have a 25 uh, megapascal material, concrete, for instance, the uh, soil freaks about 800 kPa. The other thing that has we have developed along a long time, was multiple phase grouting. All the first nails that I have been designing and supervising construction, we did in one phase. Now we prefer to do in three phases, and we found out we have an increase in soil nail friction of about 50%, minimum 50%. And how we do that? We do the drilling, we do the grout pressure initially uh, without any pressure grouting. Okay, then we store the nail with a minimum of three grouting pipes, and we do the first at the end of the nail, then we do the middle phase in the middle of the nail, and the last phase. But doing that, which doesn't cost that much, the cost of this is very small. In most cases we have an increase of, say, 50% of to 100% in in the behavior of the nail in terms of friction. Okay, so this is what we do today, and I think the behavior is much better. Finally, I'd like to, this part I'm finishing the initial part. And of course, I'd like to acknowledge the help I've got from DiviDag. They supplied me with information which I'm showing you. And also a friend of mine, who is a contractor, ZR. We have been working together for over 30 years on multiple solinating walls. And this is my uh, contact details. So if you have any question about that, any question, you may contact me later on. Now let's go to the second part, which is going to be uh, tiebacks. Just a second. Okay. Well, uh, as I've said before, the tieback wall usually has a thick 30 centimeter thick wall, concrete wall, and the tiebacks are pre-stressed to a working load which is round about the half of the maximum yields of the steel used for these ground anchors. And this is a story I'd like to tell you, which is interesting about the first tieback I've ever heard. This was my professor at School of Engineering. His name was Costa Nuni. He was a very experienced engineer, and in addition to being a professor, he was the head of a big geotechnical company in Rio. The name was Tecnosolo, and uh, I took two. I remember I took two subjects with them. The first one was about photography because he was very much interested in photography in physics. He used to give a class, a course on how to photography. And then later on in the fifth year, I took a course of soil mechanics and foundation engineering with him. And he used to talk about the I talk a lot about tieback walls. That's how I learned. And then he used to say that he was the first, one of the first, or perhaps the first, we don't know. For me, it's the first to design a tieback wall in 1957 for this hospital. This is this hospital here is a very old hospital in Rio, and just a sec. It was built in 1840 or in the 19th century, uh, and there was an expansion works in between these two old buildings and the new buildings which is behind. And this took place in 1957, as he uh, told us. And he told a lot of things about this experience. And what happened was that this information was lost. I worked in Technosolar many years ago, and then I talked to uh, my colleagues there if anyone knew where this first tieback wall was built. And then one of my colleagues he told me, I know where it is. Let's go there. And we found it. This was 3 years ago. We found this wall just very close to the new building. It was in between this old building, which is here, and the new building. And this was more or less the dimensions of the wall. It's 6 meters high. And in a very, today, since they built this here, they will have only 2 meters uh, the space in between the wall and the building. And so 3 years ago, we went to that hospital. It took me hours to convince them that I want to see the this wall. And this is my schoolmates, which was we worked together in Technosol, and he knew where it was. And this the lady from the hospital that accompanied us to this place. And what we found, I remember very much that Professor Costanone used to say that this first wall, he was very much afraid of doing that because he didn't know the behavior, creep behavior of these ground anchors. That was absolutely new to him. And he designed, instead of designing a wall, he designed simply a grid because the material he was hard, and he thought this would be okay. What we found, we have some pictures, and we have published a paper. The paper was published in 2023, so 2 years ago, in Soils and Rock. It's a journal, and we found a lot of corrosion. Okay, and also this first wall, they use those concrete rebars, which of course is not very good, and no corrosion was no corrosion protection was used in this first wall. And so this experience was the 1957, the first tieback wall in Rio. Okay, and later on, Professor Nunes and Venoso, they published a paper in 1963 of how to do the calculation, etc., in which they use a wedge method, which I'm going to address. And later on, in 1967, we had a lot of slope failures in Rio de Janeiro, and so the Mayo created, the Mayo at the time created what you call today the Gel Rio, which is an authority that looks after the slopes in town. So they have published the manual, which I was one of the authors, slope manual, and all the protection, etc. They also they issue rules and specs how to deal with slopes, etc., etc. So it was a major advancement here in this in there in Rio, and finally, one of the major milestone was 1984, the perhaps the highest wall that I've been involved in 1984, 35-meter high wall. It was a milestone. And so what Professor Nunes developed was, first of all, we have to do in construction in stages. We have to take the wall from the top. Remember that before 1957, for us to put, a concrete wall, we had to excavate a lot, much more. And by doing this kind of tieback wall from the top, we could limit the amount of excavation, and there was a lot of advantage. So these are kind of wall that's being built. So here's the construction. The construction is in stage from the top down. Okay. Also, uh, this was his idea. He developed the niches in which we leave these kind of berms to stabilize or not to allow uh, as I'm going to show you later, an accident taking place because of lack of these niches. So it's slow process of excavation, but safe. And so here another example, excavation in niches, and then the wall is being built also in this situation here. And this is much later in which they use precast elements for this. But on the other hand, they used these multi-strand anchors, which at that time, perhaps not today, if you use a proper construction material, but at that time was a big problem with corrosion. Uh, so, uh, different types of failures that can take place in tieback walls, like base punching. Okay, I never seen this taking place, but it can take place, and I'm going to let you know which solution we may use when you have this kind of problem. Toe failure, I've seen a few. I'm going to show you. Generalized failure as well. And well, I've never seen a whole failure like that. You know, uh, these are generalized failure that took place. Uh, one of those I've seen close to a railway. Okay, and this is mainly due to corrosion in the nails. Yeah, you see here what happened. It's a video. It's 5 years, 7 years ago that took place. Okay. Ankle failure. Here's an example that I've seen. Uh, I This is in between. It's about 200 kilometers from Rio in a motorway, and this panel I've seen this many years ago. Unfortunately, I didn't have the camera where this panel failed. I remember coming here and I saw this panel on the road, on the pavement, and this was a non-core failure, definitely. Okay. Uh, Excessive deformation. This another wall. As you see here, there was this tied back wall which presents excessive deformation, and we could see from here. Okay. And some generalized failure. Okay, wedge, slip circle that can take place, and we'll probably have something to show you. How to do a stability analysis. In the past, while I was in school, and until the computer programs became much better, which they are today, we only used the wedge methods, which was very simple, okay? And today we can do very easily a global stability analysis. But for years, we just used the wedge method. And this was the Nunes, my professor Nunes and Veloso, both were my professor at the School of Engineering, very good engineers. They passed away long ago, and they came up with the idea of using a kind of wedge method to analyze the stability. And later on, much later, the Germans, Jelinek and Ostermeyer, developed something a little bit more sophisticated, in which they had two wedges. The Brazilian just had one wedge, and but I can say that this worked very well for many years. This is the wedge method, which has been developed by them. Very simple equation, and we can take into account water, etc. etc. Perhaps it's not the same equation that they propose, but it's the same method. Okay, it's a different, slightly different equation. And when we didn't have computers, that's what we use. We don't use this anymore. Today, this equation was proposed by Hook and Bray, same methodology. And today what we do is global stability because we have programs that can do that, and I'll show you some results. In those days, to do an analysis of two tieback walls are nearly impossible. Okay, so they were designed separately, which of course is not the best way to do that. And today we can do the stability analysis, which I'm going to show you some examples, and also we can do finite element analysis to take into account deformation. To look at deformation today is very easy. This is a analysis that I have done long ago with Plaxis. It's one of the best programs. We still use it. Not this version. We have much better version today. And so this is a finite element mesh, and we can look at the deformation and also vary the working load on the ground anchors, on the anchors, in order to limit deformation or increase deformation, etc., etc. So, so that's very easy to do, and today that's what we in most designs we do an stability analysis, but we do also deformation analysis. That's very straightforward. So we can calculate moments, we can calculate the axial forces on the anchors and check the design. Another very important thing that we have in our standards in the manual, which I helped to write long ago, the maximum distance between the axles, if they should be a minimum of 5 meters deep, and also the maximum distance between the anchors should be more than 6 times the diameter of the borehole, or also greater than 1 meter. Okay, uh, so this distance in between the wedge and this line, which we start to put the bonded length, is point 15 of the height of the wall. Okay. Also, in a plan view, we have this minimum distance should be 8 times the diameter, more than 1 meter. The other thing that we use a lot in order to avoid a toe failure is micropiles. Sometimes when we have a loose material or softer material here, let's say less than 10 SPT, less than 10, that's what we usually do. We put these micropiles in order to support the weight of the concrete wall. uh, some examples. But before we go into the examples, let's have a 1 minute or 2 minutes break, and I'll come back in 2 minutes. Okay, just to relax a little bit. Okay, I'm back. Well, let's talk about the examples. Oh, forgot this part. Okay. This road immigrants highway from São Paulo to the coast. They used a lot of these tieback walls, but as I've said to you before, they use a lot of these uh, multi-strand anchors, which it was a big problem. I've seen too many failures with these anchors. Okay, so that's why it was very scary when I see these photographs. I've seen too many failures. This is the a very high wall which I've been involved in 1984, and at this place at Carey Beach, and this was a mix in between uh, tieback with anchors at the bottom and soil nailing at the top. It was a mixed wall, which was we designed. And this kind of generalized failure that I worked in 1990, uh, by this time, the computer programs were very bad, and I had to analyze to use my own program. So I visited this site. I was invited as a consultant to investigate the cause of failure. And this was being built, and there was this kind of generalized failure after some rain. And in those days, I prepared this kind of program. It was an existing program, stable, which was developed at Purdue University, and I got the source code in Fortran. I was very good in Fortran in those days, and I I managed to install the effect of these tiebacks. They didn't have tiebacks. I managed to install that later on, which I'm going to show you. And by using these parameters and raising the water level, uh, we came up with the conclusion that it was very unstable. The factor of safety was very, very bad. It was a poor design. And this, the yellow line in Rio de Janeiro, 1994, there were all these, this was a amphitheater, as the tunnel engineers used to call, and it was designed with all these walls, and we have some uh, soil as well. This how it is today, and I worked at that construction as well. And this is another example in which instead of increase the thickness of the wall, this kind of concrete plate could be used to distribute the distribute the loads on the wall. With this kind of solution, we reduce the amount of concrete that is being used. And this is the yellow line. There was a big failure during construction in 1995. And I had the opportunity to analyze this. And in those days, of course, we didn't have the program that we have today. This is how the failure took place. And so I did an analysis, and the design analysis was like that. Any value, the soil is very hard, in between 28 and 40 SPT, no water. We didn't find any water here, and these were the parameters that I have used to do a back analysis, and we had laboratory tests that confirmed those values. It was mainly sand saprolites, and the factor of safety at the final stage was 1.4. So why this failure took place? The design was okay, but the problem was the construction method. It was not clear on the design documents that the designer asked for niche construction of those niches which I've shown you before. And what happened was that during construction, the contractor excavated uh, some 100 meters in one time at a time without leaving the niches, and the failure took place. So with only two anchors levels, which were taken from the top. This wall was taken from the top, and the factor of safety at this stage was only zero point 0.9. So the excessive excavation without the niches, and then it was reconstructed, and so this is the part that failed, as you see here. We still see this today. Unfortunately, they lost some uh, some space on the top here because of this. That was a decision. And in 2011, I worked on the design of this very high wall in Toquepala in Peru. It was for a mine, the Southern Peru Copper Corporation, the owner of this mine. And this is for the rock crusher, which was going to operate this position here. So it was a big challenge, uh, but very interesting. Uh, which I'm going to so this was the stability analysis I have done. In those days, I have developed this program, which I mean not developed. I entered the anchors and nails in these programs. In this Purdue program was stable, and I decided to call it R stable. It was before very good programs that we have here were developed. Now we don't use this anymore. And this stability analysis without anchors, of course, is very low, 0.34. With anchors and no seismic acceleration was 1.94. And then by using that coefficient of PGA, acceleration, which very very simple to do. And in Peru, it's zero point 0.3, so it's very high, very high. And we read the factor of safety during a seismic event could be 1.4, but it could be acceptable. So that was the design, and we had a big discussion be, with the owner about which working load, the factor of safety we should use for the working load. And this was the no we normally use in Brazil. We used in Brazil it was 1.5. In Hong Kong is 2, but the federal highway is much less, only 1.33. I would be very happy to use one of those values, which I think is very safe, but I'm not very happy to use 1.33. But there was a big discussion, then we won. We used the 1.7, more or less 1.7. And also we did, uh, I spent nearly 2 weeks at the site working on the design. And we did deformation analysis with Plaxis also, and by doing that, we could calculate the moments, etc., for the structural engineering analysis. Here, the construction, okay, the excavation taking place. It's a very dry location, okay, in Peru. It's on the top of the Andes. The altitude is about 3,000 meters. So I remember we had when I first came to the site, we felt the soroche. Soroche is a Spanish word that means the headache that takes place when you are without oxygen at this altitude. And very dry. The amount of rainfall that takes place here is not more than 3 millimeters per year. So that's why we didn't care very much about corrosion protection, because no water, uh, also in a remote site without pollution. So we didn't care. And also, this structure is not permanent. It's going to be a few years there, 5, 10 years, and then we're going to decommission this structure after some time. And this is another very interesting work we have done. Uh, this is an old road that took place in 2018, and this is the old wall. And there was a big failure at this site, this series of walls, which I'm going to show you. And the failure took place because of corrosion. I have no doubt. This is the anchor corrosion that we could see when I visited the site. And we did design review. Okay, there was a designer. The guy designed very long anchors. You see how long they are. And this is the stability analysis now with these new programs that we use today. This is a slide program. And as you see, uh, we, our recommendation for the construction was that these free length were too long. No problem, but of course the cost would be much higher. Also, we did Plaxis uh, two-dimensional finite element analysis to check the deformations. Okay, and we this is our conclusion. Our main conclusion is that the tiebacks are safe but too long. I worked in Hong Kong as well, and long ago. And Hong Kong, they didn't like very much tieback walls. I'm going to talk a lot in the next hour about the soil nailing in Hong Kong, but they didn't like tieback walls because they thought they would have to measure the tensile stress on the anchor throughout the life. This is not necessary. Okay, provided you do a proper design, provided you use safety factors, uh, of 2, of 1.7 or 1.8, it should be okay. And there's very little creep if you do that in uh, residual soils. So we have a lot of experience in residual soils, and also in Hong Kong they have lots of residual soils. But even though they are very conservative with using this, and this is one of the few tied back walls they have in Hong Kong, which I visited. Okay, and so they had this precast element, but they do measure for a long time. They do measure uh, stresses on the anchors, which is not absolutely necessary, provided you have experience with that soil. And this is one of the most complex walls I have designed last year. It was for Gloria Hotel. Gloria Hotel is over 120 years old, very old, and so it was recently renovated, and uh, the problem was they have in the hotel 6 or 7 uh, walls which had to be renovated, and we didn't have any parameter. We didn't have any design from these walls because they are too old, 125 years old, and this was one of the most complex that we have designed. It's a 6.5 meters wall, high wall, but we have here the foundation of the building, so we could not put the anchors where we wanted. We had to find out a nice location to put the anchors in, and we have to use this vertical anchor in order to stabilize this wall. This is very complex, and this work hasn't finished yet. We still visit the site from time to time, and uh, last month I was there. Anyway, final remarks about this tieback walls. We have an excellent experience since the 50s. Okay, used as a rigid structure. Corrosion is in unprotected multi-strand anchors was a big problem, and I faced many problems with that. Now, DVDAG, for instance, as a manufacturer, they have a solution for that. I haven't used that yet. We have to consider water factor for rainfall in locations where we have high levels of rainfall in the stability analysis. Usually I use zero point 0.2 or zero point 0.3. Okay. Today we can design. That's what we do. We design a limit equilibrium method by using one of these slide programs, which is available. Very good programs, and also we can design, and we usually do finite elements in order to check the factor of safety and also to check deformation and moments on the wall, and design for construction stage. As I've shown you, if you miss that, you may have a big failure like the one I have shown you. Okay, so this is a summary of our uh, long experience with that. And now let's go to the final part of our talk, which is soil nailing. Okay. Uh, we're going to talk about the use of soil nailing, the origin, the concept, comparison with tieback walls, and analysis, limit equilibrium, and finite elements. Okay. Application. We use a lot of soil nailing for existing slope and excavation as well. So both applications. And the construction phases usually are we excavate one bench, usually 1 meter deep bench. Okay, we put the nails in, but we use a borehole, usually 75 or to 100 millimeter borehole, where we store the nails, and then we can use sprayed concrete to prepare the facing. Today, there's a trend in some places where you have an inclined facing, not to use sprayed concrete because of the appearance, and use something else, vegetative solution, which I'm going to show you later. So here are some construction phases. As you see here, this being excavated, so nails are being used here. This is a yellow line. That was 1995, I remember. And also, what's the difference between reinforced earth and other types of reinforced soil reinforcement? Reinforced earth is usually from the bottom up, okay? And it's for, as we very much use in abutment, in bridge abutment, in order to avoid the inclined slope, okay? So also called MSE wall, okay? Geosynthetic reinforcement also, we can use embankments, okay? Very much used. And soil nailing is just the opposite. We take from the top down, okay? Can the wall of soil nailing can be vertical or inclined, very easy to do. And as I said before, the difference between active reinforcement for tieback walls and passive reinforcement for soil nailing. Soil nailing, we do not pre-stress the nail. And how does it mobilize its friction? When the active wedges tends to move. A small, a small movement would mobilize friction on the nail. And not applicable where we can't use soil nailing, where a 1 meter bench cannot be excavated. For instance, if you try to do it beach sand with no cohesion, no way. We try to do in soft clay where you can't excavate 1 meter, no way. You can't use that in this type of material. So you need not with soft clays, not with uncemented coarse sand like beach sand. What are the advantages? Mainly economy. In most cases, a wall like that, a soil-nailed wall, would cost a half of the price of a tied back wall. Construction time is much faster. Wall inclination, very easy to deal with any wall inclination. In most cases, the behavior is very, very good. Uh, where you have a problem with excessive displacement, They can be controlled with additional anchors in order to use a mixed wall. Okay. And what were the milestones for this kind of wall? The first publication about this type of wall took place in France, Versailles Chantier Wall, in 1972. Then, in the 70s, it appeared many design methods, which I'm not going to address with all the details because they uh, no longer needed. No, today we use just one of these stability analysis programs. But in 1979, that was before these programs were developed, there was a German method, Davis method in 1981, multi-criteria, which the French method developed in 1983. In 1991, the French carried out a research program called Cloutaire, and this was a major milestone because they did a lot of analysis, a lot of experiments, field experiments, laboratories experiments, and that was a big, pushed ahead of the technology of this. Nail installation. Usually we use we tend to use a big hydraulic rig like that, okay, or can be a pneumatic rig, which I have used in many cases. Uh, so this crawler rig is usually on the ground, uh, but if you need to scaffold, you can use something like a very light drill rig, which I'm going to show you. It can be pneumatic operated or hydraulic operated. Nail head details. We have different ways of doing that. This was the main, most uh, most sophisticated uh, head with two steel meshes. Okay, so this a lot of concrete. But today I've seen with success of we call it the chicken feet. Uh, uh, we just bend the nail here and we use a much smaller shotcrete. In many cases, this would work nicely. Although, of course, I would prefer to have this, if we're using DVDAG, of course, I would prefer to use this plate and nut. Okay, but this is also possible and have been successfully used in a few cases. Okay, also uh, I've used also lots of steel fibers instead of steel mesh. Okay, but now the trend when you have an inclined facing is vegetation, as I'm going to show you. So these are recent trends for nail head details. So we have here concrete, sprayed concrete with fibers, steel fibers, and here how to put the plate, etc. We just increase the thickness of this area in order to have this wall. Also, we can use the chicken feet, as we call them, uh, by just bending the nail. And here's some examples from a few countries that I've been working in the past, like in France. This is this laboratory, sorry, this bibliography information. This is the first published wall, soil nailing wall, Sol Clouet, in Versailles, close, not very far from Paris, in which they used and this is very clear that was designed by a tunnel engineer. Why? Because they use two layers of concrete. The primary layer, which is very normal, very common in tunnel, okay, in ATM tunnels, and the secondary layer, which is today we know that is not no longer necessary. But what's interesting is they use very short nails, like 4 meters and 6 meters, although the height was very high. So they should have a very good material here to. It's not the wall that's reinforcing. They should have a good material. This is another example from Mur d'Opéra de Montpellier, qui est also in France, and you have here it's a fill. Okay, here's sand. Okay, they used very small, very not very long nails. The length was only 8 meters for an excavation depth of 21 meters. The spacing is here, and the cornier batik. This means these are driven driven steel driven steel sections, not like an L section. Cornier is an L section in English, and uh, very interesting. And this was very long ago in the 70s. Okay, and so now some lots of examples of from Hong Kong where I also worked for some time and I got a lot of experience in there. This, as a matter of fact, this is my name. I'm very proud. I'm very proud that I have a Chinese name, which is Onpato. Onpato. Pato is the name of a Brazilian football player that played in China. So they had this name Onpato or Pato, which is not very far from Alberto. So they gave me this name, and the best, the nearest they could come to my last name, my surname, which is Ortigão, is On. So this is On pa to. As you see here, on is not very difficult to draw, pa as well, but the toe I never managed to to write the toe. Toe is very hard. But anyway, uh, this one of the sites I've been in Hong Kong. I was working as a visiting professor to the uh, City University of Hong Kong, and I visit many sites with the GEO. GEO is the Geotechnical Engineering Office of Hong Kong, and they were very advanced in these techniques, and I learned a lot from them. One of the sites, very interesting, these sites in which they used bamboo scaffolding. Okay, very interesting. I've never seen so much bamboo being used on construction sites, and you see here all the scaffolding is made with bamboo, and this is one of the very light drill rig they used to put the nails in. Okay, so you see the bamboo scaffolding here, and this is a platform. The platform is made of steel for the drill rig. These are also a pneumatic light rig in Hong Kong, as you see here, to put the nails in. Okay, and this is another construction site at Castle Peak Road. The nails that nail head in niches. They could uh, they could hide the nail head in these niches. Okay, very interesting solution. And this is in Kuala Lumpur. I also did some work in Kuala Lumpur in those days. Uh, I helped them with they want to develop a system for early warning system for slopes, and I did some work in Kuala Lumpur in Malaysia. And these are very interesting. One of the first facing which I saw to be vegetated instead of using sprayed concrete. So I learned from that, and today we have designed a few cases with this solution. Uh, I also worked in Canada, in Vancouver, between 1991 and 92 as a visiting professor of the UBC, University of British Columbia. Also did a lot of work in with soil nails, uh, and this kind of temporary shoring in Vancouver. Vancouver has a very high strength soil. You can't do any SPT. You need a rotary drill. So we don't have any soil problem in Vancouver. This is also in Vancouver city center, which I've seen stabilize this wall with props. Okay, but there are soil nearly on the other side. This side of the building, they for some reason they could not put the nails in, so they have to use the props. The other sides they could do the soil nailing, and this is another example. As you see here, the soil is very hard, so you didn't need a lot of nails, or the nails are not very long, but very difficult to find this kind of very hard soil, not nearly rots. Okay, And some examples, yeah, this is an example from Argentina. I was invited to do some work on this, uh, the accident that took place, that was a temporary shoring in a building in Mendoza. And there was this kind of failure in which I visited the site, and we used, we stuffed the failure, that uh, volume with bags, sand-filled bags, and then we did the soil nailing afterwards. We sprayed concrete and did the soil nails afterwards. And now some Brazilian examples. Uh, Yeah, as I've told you, the first tieback was 1957, and there was a big development, and soil nailing was used for the first time in 1970, a little bit before the French have developed the technique. But why? I'm going to show you. Because of tunnel engineers, they had the idea and just uh, spread the technique from from within the tunnel to the portal. Okay. In 1984, it was that very high wall, which was involved in 35-meter high mixed wall, which in 1989, that's when we started doing all those tests to do analysis and optimization, which we published in the London in a conference in London later on. So this certainly was the first time this technique was used. And this was a tunnel being constructed by the NTM method. And the contractor was using these, boats, rock boats, etc., here in the tunnel to stabilize the uh, the excavation, and they decide to use the same technique on the portal without any calculation, but it worked very well. This was a company that no longer exists, but I was a good friend of the owner of the company, and he told me all that, and we later on we use the same technique. So this is another example in São Paulo where this excavation was done, and they put these 4 meter deep anchors. This was done at the time without proper calculation, because he came to me in the early 90s for me to do some calculation for him. But until then, they had already done some very good work just by experience. Okay, and this is bridge abutment protection in phyllites. They found out the phyllites were not behaving very nicely, and they put all these anchors in and worked very, very well. And so this is one of the initial projects I've done with them. This 30, 35-meter high wall with nails and type soil anchors, and we did some stability analysis. But at the time, it was scary because we didn't have all the data, uh, and for soil properties and soil friction, soil nail friction. That was the key parameter that we estimated. So, but it's there, That's the wall during construction. After that, there are some buildings in front, no problem. Another wall from also in São Paulo uh, with very uh, length of these nails. Okay, this one of permanent shoring, and this is when the program was ready. The our stable program was ready to use, and this was one of the uh, major project that I've done with this contractor. Okay, but then Gel Rio, which is the uh, organization in Rio de Janeiro that looks after the walls, they hated soil nailing. I remember when I came from from Hong Kong, from the experience I have had, and also Canada, etc. And I had the program that I could use to analyze stability of soil with soil nails. I went to see them. I gave them a presentation, and then they said, "Ah, okay, we're going to do uh, some experiments before we adopt the the technique." They didn't believe. Some of them were, were scary about using this technique. So they gave me a wall to do some experiments. I was a professor at the university, so I invited. I had some people from the university working on this project with me. It was a kind of research project. There was a tied back wall designed by Geo Rio, and they gave me a 20-meter length of this wall at the end. Okay, it was in a hidden place, so if they were so scary, they didn't want to do this wall in an open space for anyone to see. So we did in a hidden space, hidden area. It was some 20-meter long, and we did a lot of experiments in order to do this analysis and uh, you know research. There was one MSA thesis which was done. There was one student doing that with us, and it behaved very well. We managed to measure deformation. We measured this. We measured that. We did pull-out tests, etc., etc., and it worked. Later on, another university in Rio also had the same idea, a friend of mine, former professor Alberto Sayon, and he carried out also experiments in 1994. And then after these two experiments, you already decide, we're going to use, and now it's widespread. You know, I'm very happy that I was able to introduce this technique to gel reel. And now this is the what we do today. The idea is when we use shotcrete is not nice. You know, if you have a big wall with shotcrete, it's not very nice. And when we have a slope, which is inclined, like this one, okay, we may use something much user friendly, which is the green soil nailing. I've been working with this company is also belongs to a friend of mine, and we have been working together for years now, and we developed some solution like that, you know, the green soil nailing, and this is an example with the slopes 65 degrees inclined, 10 meters high. And my friend's wife, she has a background in agronomic engineering, the wife of the owner of this company. And she developed some techniques in order to do the surface conditioning and to make sure that the vegetation is going to grow. So she developed this kind of small holes. They do it by hand, okay? And she says that since they sprayed after this, they sprayed water and sprayed the seeds here, and these small holes, they keep the vegetation there. They keep the seeds. They keep some water, and so the vegetation grows. So this is the technique they have developed, and I only did some analysis, and this is the biomesh we use. Also, it was developed by this company. This biomesh is very dry in the beginning, but soon after, in a few months, that's what we get. Much more beautiful, and this technique takes, it's more labor intensive than nearly shotcrete, but it's much more beautiful, much more environmentally friendly. And finally, this is the main reference in America, Soil Nail Walls reference manual developed by the Ashto. So it's not very different from what I've told you, and you may you may be interested in looking at this reference as well. Uh, let's have a look at the design, how we did the design stages. So We do the, of course, we have to do a very good site investigation. Pull-out test, that was the Achilles heel in the beginning, but later on we developed those correlations, which came into very handy because we still use those correlations and they do work for a preliminary analysis. Stability analysis, when I started, we didn't have the programs. I have to write my own programs. It was a very difficult task, and I have some students helping me, students from the university, but it worked. Now we have very good programs, so it's very easy. Deformation analysis also, now it's not difficult to carry out. I have used Plaxis a lot to do that. And site investigation, what you have to do, of course, you need stratigraphy, you need groundwater, you need the strength parameters, and you need soil nail friction. Okay, we have done pull-out tests. I have tried to do pull-out tests before a construction. It never happened, except at the Brazilian Underground, which we did the soil nail pull-out. We did a pull-out test before we designed some structures there. If you have different materials, you can, work out this kind of excavation to do the pull-out test in order to come up with the design parameters. This is one of the setup, as I've shown you before, with the jack, with the load cell, with the dial gauge to measure displacements. This is something which I've seen in France. They adapted this this rig. They adapted with jack here in order to do testing, very quick testing on nails. Okay, as you see here. So the jack, and I don't remember. I don't think they had a load cell. They used to measure the loads with the jack, but this just for some testing. It's later on. This is the friction design chart which I've shown you before, and this came in handy, very helpful, and most of the designs I have done in, since we developed this was with this correlation. It works, at least in all the soils I have done. Yeah, I have worked with. So multi-stage grouting, this is the new technique that has been developed by a friend of mine, and we know that is much better. If we do two phases, usually we double, minimum 50% of additional nail friction. Methods of analysis. There are several. As I've told you before, the German was published by Stocker and other people in 1979. Davis by Shen and others. Schlosser, 1983, developed the multi-criteria. Kinematica by Giron, all the French, in 1988. Cardiff was developed by a British guy, Bridle. Yield also a method developed by Antoine. So, and I developed my own, which I don't use anymore, which was the modification of that program to install the nails. I did that in 1995. And though, so how this method differ? The German method, they used wedges, okay? The Davis method used a parabolic failure surface, and Cardiff used a log spiral. Multi-criteria used a circular or polygonal curve, but was the first one to take into account the shear. Most of those methods before, they used only tension, and Cardiff decided they came up with the shear shear load as well. Okay, the tensile forces, it's very easy to take into account. And what we do is, if we have the friction, unit friction, this is the diameter of the borehole pi, and this length, the length in the passive zone, which is LP. So that's how we calculate tensions. And shear forces is a little bit more complicated. I'm not going into these details because most of the time we don't use the shear force. I'm showing you. Uh, when we definitely use the shear force, when you have large diameter mini parts, for instance, this is the case that shear force is going to be important. But in most cases, if you do use the shear or not use the shear, doesn't make a big difference. So in most cases, we just use the tensile forces. And uh, then there were lots of programs that were uh, prepared. These were initial programs. Now we use much better programs now. This the program that I've developed in 1994, and other programs that have been developed in France. Tauran, Clouage, Nixes, and Prosper, all developed in France. Tauran is still available, but it's a very good one, but we prefer to use this slide, which we use for all slopes, not only for soil nailing. So slide program is widely available. It has we can do the analysis. So this is an example of analysis of a homogeneous slope. This is the factor of safety with we easily calculate the factor of safety without the nails. Then we put the nails in very easily with this program, and we can increase the length of the nail. We can change the parameters, the soil nail friction, etc., etc. It's very straightforward. So we just come out with this pop-up screen where you can modify very easily this. You know, it has a very user-friendly interface, which in the past we didn't have. My program, the one I had, was a terrible interface. And then we calculate the effect of nails, and it gives you the factor of safety. Usually, what you look for, it's 1.5. You can change the parameters. You can have water level. You can have pore pressure factor, which I do use in areas where we have severe rainfall. I usually use zero point 0.2 or zero point 0.3. It works. And also, which was very difficult to do in the past, now it's very easy. Deformation analysis in some cases is very important. And the very well designed soil-nailed walls. Usually, the horizontal deformation at the top is less than 0.3% of the height. So this is the goal. Okay, and if you have uh, depending on the length and how you put the nails in, although you may have the same factor of safety. That's a question I put for you, and I wonder if you could have a look and answer this in the chat. So these are walls which have been designed for the same factor of safety of 1.5. However, this one has all these have the same length. This one, the length increases with depth, and this one, the length increases with height. So my question for you is, which one of these walls would deform less? Okay, I want to answer you that now. Let's see if you answer this question in the chat. So the other thing that sometimes I have had in the past was design for deformation. This is not very common, but sometimes we have a situation like that. So you have a kind of a load here. You have to to spread footing. For instance, this could happen. Also, a very high lorry, a big lorry here, applying a big load on the top of the wall, and then you have to design for deformation. And usually, when you design for deformation, today you can take into account you can carry out the finite element analysis. But this finite element analysis for this application is not more than 20 years old. So before that, we didn't have these techniques. So wall deformation is different from soil nailing and reinforced earth. So in reinforced earth, usually you have the maximum deformation in the middle of the slope, or perhaps a little closer to the bottom. And soil nailing you have at the top because of the ways of the consumption method. Uh, Today is not difficult to carry out horizontal displacement analysis, okay, by using finite elements. And these are ways to limit deformation. For instance, to use a mixed wall in which here you have a soil nailed wall, but here to avoid deformation of this part of this footing, you build a tie-back wall to limit deformation. This is another idea. You have a mixed wall in which you may have uh, soil bunkers at the top and nails at the bottom. You can do that. Drainage. Drainage is very important. What you have to do, you always need a channel uh, at the top, a channel or ditch at the bottom, and these channels would convey water out. Will not try to avoid this. Also, you can have this kind of French drain in order to catch the water level in the back. Of course, this cannot be very deep, but I have done this 1 meter, 1.5 meter deep in some cases. We need the facing drainage either by whip holes like those or by using, which I have done in the past many times, by using a geosynthetic filter, a geosynthetic for drainage, which catch the water that comes through the face and conveys to the bottom where you have a drainage pipe. Deep drains can be used as well. I have used it many times, but they don't last very long. Usually, deep drains deep drains are a temporary solution which may last a few years, 5 years, but most of the time, I've seen this many times. After 5 years, maximum 10 years, they clog. Okay, they do not work. Even if you do maintenance, you wash these with water jet, they may clog. These are some details of how to do this uh, subhorizontal drains with a 50 millimeter diameter PVC tube and 2 layers of nylon mesh. This is the best, better than using non-woven geosynthetic because non-woven geosynthetic may clog earlier. This is the long-lasting one, but even though should not use for permanent drainage. Different types of face drains using geosynthetic, as I've shown you before. Usually these stripes, the distance 1 meter from one to the other, or whip holes, very common. Okay, and instrumentation. Usually we don't do a lot of instrumentation anymore. We did in the past for research instrumentation in a few walls in which we have to analyze to prove gel real in the past that it was a safe solution. In the past, we have done with inclinometer, with strain gauge nails. We put the strain gauge to measure the distribution of force, stress, tensile stress along the nails. And also we use some surface marks and piezometers. So this is the typical instrumentation, but in most cases, it's not necessary anymore. So we come to the end of this seminar. The conclusions are we have seen applications, near application to slopes and excavations and also tieback walls. They have been used since 1970. The first publication was by the French in 1972, but my Brazilian friends have used that a little bit before, but without proper analysis. Analysis came much later. Okay, economy in relation to tieback walls usually is half of the price. Okay, proven design methods for stability, for deformations, and that's it. So these are the conclusions. Finally, my acknowledgments of my friends who helped me from DVDAG, from ZR, soil nailing. We've worked many many years together. And GeoGreen, the one, my friend who developed this technique of ensuring that vegetation is going to grow and last. And for some application, it has been much better than the use of sprayed concrete, much more user friendly. And finally, of course, I repeat my contact details. Should you have any any issue, any question later on, you may contact me. I'll be very happy to answer any question. So that's it. Let me see if uh, there are uh, anything in the chat. If you'd like to uh, chat, no, sorry, I don't see anything here. So if you don't have any question now, you may have in the future, and you may contact me or contact Insight Engineering, and I'll be very happy to discuss any issue that you may uh, come up with. Let me see. Ah, no, there is. Sorry. Equal nails is the best, but the one who developed less deformation is the one with a longer nail at the top. Okay, and why? Because you're going to have a much more higher force, tensile force at the top, where most of the maximum deformation takes place. Okay. Anyway, thank you very much, and I'm available on the other side of the line should you have any question. Okay? Thank you. Okay. Bye bye. Thank you very much.